Let me start by asking you a question. Are you moving right now? And the answer, at least according to physics, is kind of yes and no. I know that sounds weird, but it all just depends on your point of view.
Okay, picture this. You're on a bus. To the person sitting right next to you, you're not moving at all. You're perfectly still. But to somebody standing on the sidewalk watching you go by, you're definitely moving. That bus or that sidewalk, that's what we call a reference point. And honestly, it's the absolute key to describing any kind of motion.
Right, let's make this real with a simple journey. Now, to describe a trip, physicists use two really important tools. They sound similar, but trust me, they are totally different. Distance and displacement. This is our first peek at a huge idea in physics, measuring something with direction versus measuring it without.
So first up, we have distance. This one's pretty straightforward. It's the full length of whatever path you take. It's every single step, every meter, every little detour you make. It's literally the total ground you covered. So let's say an object travels 60 kilometers out from where it started, and then it turns right around and comes 35 kilometers back. To find the total distance, you just add it up. 60 plus 35, that's 95 kilometers. Easy enough, right?
But now we've got displacement. And this is where things get interesting. See, displacement doesn't care about the path you took at all. All it cares about is where you started and where you ended up, measured in one perfectly straight line. For displacement, direction is everything.
So for that exact same journey, remember, the one that was 95 kilometers long? Well, even though the object traveled all that way, its final position is only 25 kilometers from where it began. So its displacement is just 25 kilometers. So here's the bottom line, the really crucial point. Distance is the long, winding road you actually traveled. Displacement is just the as-the-crow-flies shortcut from your start point to your finish line. This means you could run a whole marathon, a huge distance, but if you end up right back where you started, your displacement is 0. Okay, so we know how to measure the path, but what about how fast we're moving along it? Well, this brings us to another pair of ideas that sound almost the same but mean very, very different things in physics: speed and velocity. To really get this, let's use an example straight from our source material. We've got a swimmer, Usha, in a 90-meter pool. She swims all the way to one end and then immediately swims all the way back. All in all, she covers 180 meters in just 1 minute. So, what's her average speed? Well, that's just the total distance she swam divided by how long it took her. So that's 180 meters divided by 60 seconds, which gives us a speed of 3 meters per second. Yep, she's definitely moving. But then there's velocity, and velocity is different. It cares about displacement, not distance. It's asking a totally different question. How quickly did your position change from start to finish, and in what direction? So what was Usha's velocity? Well, think about it. Since she ended up in the exact same spot where she started, her total displacement is 0, which means her average velocity is also 0. Isn't that wild? Even though she was swimming super fast, her velocity was 0. That right there is the huge difference between speed and velocity. Okay, so we've got speed and we've got velocity. But let's be real, journeys are hardly ever that steady, are they? We speed up, we slow down, we take turns, and all that change brings us to our next huge idea, acceleration. Now, when you hear acceleration, you probably just think speeding up, right? But in physics, it's so much more than that. Any change in velocity counts as acceleration. So that means speeding up, sure, but also slowing down, or even just changing your direction. It's all acceleration. It's really just a simple 3-step recipe. If you have a velocity, and that velocity changes in any way, shape, or form, you are accelerating. It's as simple as that. And what we measure is the rate of that change. Let's look at a cyclist. When they start from a complete stop, 0, and they pedal up to a velocity of 6 meters per second over 30 seconds, their velocity is increasing, so they have a positive acceleration. But what happens when that same cyclist hits the brakes? Their velocity drops, say from 6 meters per second down to 4. Because their velocity is decreasing, their acceleration is negative. Now, in everyday life, we might call that deceleration, but in physics, it's all just acceleration. So we've figured out how to map the path, set the pace, and change the gears. But what if you could see the entire story of a journey
in one single image? Well, you can. And for that, we turn to graphs.
Graphs are how physicists see the whole story of a journey in a single glance. It's so cool. Like on a distance time graph, if you see a straight, sloping line, you know instantly that object is moving at a steady speed. The steeper the line, the faster it's going. And on a velocity time graph, you can figure out even more, like the total distance traveled. It's just the area under the line. The shape of the line literally tells you the whole story. All right, let's end with a question that really ties everything we've talked about together. An athlete is running around a circular track. Their speed is totally constant, let's say 10 kilometers per hour. The question is, are they accelerating? Now think about it. Their speed isn't changing, but what's happening to their direction over and over and over again?